Hello and welcome to a deep dive into one of the most fundamental and fascinating components in all of electronics, the capacitor. You've probably heard the name, and you definitely use devices that rely on them every single day. Your phone, your computer, the powerful flash on your camera, even the sound system in your car, they all depend on these tiny, energy-storing powerhouses. But what is a capacitor, really? How does it manage to store energy? And what's going on inside that little component? Today, we're going to unravel all of its secrets. Using this one detailed diagram, we will journey through the world of electrons, electric fields, and currents to build a complete and intuitive understanding of how a capacitor works. So grab a seat, and let's get started. Every story has a beginning, and for our circuit, the story begins right here, with the battery. This symbol represents our power source, and it provides something crucial called voltage. So, what exactly is voltage? The best way to think about it is as electrical pressure. Imagine a water tower. The water at the top has a lot of potential energy because of gravity. If you open a pipe at the bottom, that pressure forces the water to flow out with great force. Voltage is the electrical equivalent of that water pressure. Our battery has two ends, or terminals. The long line represents the positive terminal, and the short, thick line represents the negative terminal. You can think of the negative terminal as being packed full of tiny, negatively charged particles called electrons. It's a high-pressure zone for them. The positive terminal, on the other hand, has a shortage of electrons, making it a low-pressure zone that strongly attracts them. This difference in electrical pressure between the positive and negative terminals is the voltage. It's the push or drive that will force electrons to move through our circuit as soon as we give them a path. Now, let's meet the actual workers in our circuit, these little yellow dots, which represent electrons. Electrons are subatomic particles that carry a negative electrical charge. In a wire, which is made of a conductive material like copper, some of these electrons are free to move around. When we connect our circuit, the negative terminal of the battery, with its immense electrical pressure, starts pushing these free electrons away from it. It's a classic case of likes repel. The negative terminal repels the negative electrons. So, the electrons begin a journey, flowing through the wire away from the negative terminal. This movement of electrons is what we call an electric current. In our diagram, you can see this physical movement illustrated by the white arrows, showing the flow of electrons moving in a counterclockwise direction. But hold on a second. You might have noticed this other arrow, this big green one, labeled conventional current. And strangely, it's pointing in the exact opposite direction of the electron flow. What's going on here? Is this a mistake? Not at all. This is actually one of the most interesting quirks in the history of science. Long before we discovered the electron, pioneers like Benjamin Franklin were studying electricity. They could see its effects, but they didn't know what was actually moving. They made an educated guess. They theorized that electricity was a type of fluid that flowed from an area of positive charge to an area of negative charge. So, they defined the direction of current as flowing from the positive terminal to the negative terminal. We call this conventional current. It was a perfectly reasonable guess, but it turned out to be backwards. Much later, scientists discovered that it was the tiny, negative electrons that were actually moving, and they flowed from negative to positive. By then, the positive to negative convention was so deeply embedded in textbooks, formulas, and diagrams that changing it would have been a monumental task. So, we kept it. To this day, engineers and physicists primarily use conventional current for circuit analysis. But it's essential to remember that the physical reality is the flow of electrons. Our diagram helpfully shows both so you can see the full picture. Okay, let's follow our flowing electrons as they travel from the battery, around the circuit, and arrive at our main component, the capacitor. At its most basic, a capacitor is an incredibly simple device. It consists of two conductive plates. These are just sheets of material that allow electricity to flow easily, like metal. These two plates are placed parallel to each other, extremely close, but, and this is the most critical part of its design, they do not touch. There is a gap between them. Think of it like a bridge that's been washed out in the middle. Cars can drive up to one side of the gap, and other cars can be on the other side, but they absolutely cannot cross. This gap is fundamental to how a capacitor works. So, what happens when the stream of electrons from our battery reaches this broken bridge? First, the pile up. The electrons, pushed by the battery's voltage, flow along the wire and arrive at the right-hand plate of the capacitor. When they get there, they hit a dead end. They can't cross the gap. With nowhere else to go, they begin to accumulate, or pile up, on the surface of this plate. As more and more negative electrons gather here, this plate develops a strong overall negative charge. Now, think about the left-hand plate. It's just sitting there, electrically neutral. But as the right plate becomes intensely negative, its powerful negative charge exerts a force across the gap. It's like holding the negative ends of two magnets near each other, they repel. This repulsive force pushes on the free electrons in the left-hand plate, forcing them to flee. They are repelled away from the plate, back into the wire, and continue their journey toward the positive terminal of the battery, which eagerly attracts them. As electrons are driven off the left-hand plate, the atoms on that plate are now left with more positive protons than negative electrons. This imbalance creates a net positive charge on the left plate. So, notice what's happened. We haven't created charge out of thin air. We've simply moved it around. The battery has acted like a pump, pulling electrons from one plate and depositing them onto the other. The result is a separation of charge. One plate is positively charged, and the other is negatively charged. This is what it means for a capacitor to be charging. This separation of charge creates a fascinating and powerful phenomenon in the gap between the plates. This is where the magic really happens. An electric field is formed between the two plates. You can see it represented by these blue arrows. An electric field is an invisible force field that exists in the space around electric charges. It always points from positive to negative. Think of it like a stretched rubber band. The separated positive and negative charges are like your two hands pulling the rubber band taut. There is a huge amount of potential energy stored in that tension. The electric field is the stored energy of the capacitor. Now, what is this material filling the gap? It's labeled dielectric. In a real capacitor, the gap isn't just empty vacuum. It's filled with an insulating material, called a dielectric. This could be anything from air, to paper, to plastic, to a special ceramic. This dielectric material serves two vital purposes. First, it provides physical separation, keeping the two conductive plates from ever touching. Second, it dramatically increases the capacitor's storage capacity. This is the really clever part. When a strong electric field is applied across the dielectric, the molecules inside the material itself get stretched and aligned. These aligned molecules create their own tiny, weak electric field that opposes the main field. This slight opposition makes it a little bit easier for the battery to push even more electrons onto the negative plate. The result is that a capacitor with a dielectric can store far more charge and energy than one with just empty space. This charging process doesn't go on forever. As charge builds up on the plates, the capacitor develops its own voltage that pushes back against the battery. The charging continues until the voltage across the capacitor is exactly equal to the voltage of the battery. At that point, the forces are in equilibrium, and the flow of current in the circuit stops. The capacitor is now fully charged, sitting there like a tiny, primed reservoir of energy, held within its electric field. And that's the complete story. The capacitor will now hold this charge until we disconnect the battery and connect it to something else, like an LED or a camera flash. When we do that, it will release all of its stored energy in a sudden, powerful burst, far faster than a battery ever could. So, from the simple push of a battery's voltage to the invisible, energetic dance of electric fields and dielectrics, the capacitor is a testament to elegant physics. It's a device that masterfully separates charge to store energy, enabling the high-speed, high-power electronics that shape our modern world. The next time you see a brilliant camera flash, you'll know it's all thanks to the incredible, stored potential of the humble capacitor. Thank you for joining me on this journey. I hope you now see the world of electronics with a little more clarity and wonder.